The next page, which is really just the activity itself, the task, talks about this. In spite of the nervousness, Carlos enjoyed his first ride on the Ferris wheel. He does, however, spend much of the time with his eyes fixed on the ground below him. After a while, he becomes fascinated with the fact that since the sun is directly overhead, his shadow moves back and forth across the ground as he rides on the Ferris wheel. So this is our same Ferris wheel we talked about. 25-foot radius, the center is 30 feet off the ground, is making 20-second rotation going counterclockwise. So now instead of thinking about how far we are above the ground, which is a vertical amount, and that was a sine relationship, we're now looking at a horizontal relationship. And you can probably guess that that's going to be an x value, and that's going to be cosine. So to describe the location of Carlos's shadow, we measure the shadow's horizontal distance to the right or left of the point directly beneath the center of that Ferris wheel. So we're going to call the center of the Ferris wheel 0 as an axial amount. And then if we go to the right is positive, left is negative. So that same orientation we do with Cartesian coordinate graphing. So for instance, on our Ferris wheel, the shadow's location, it'll be 25, which is the furthest right. It'll be negative 25, which is furthest left. So in this new measurement system for question 1, if Carlos's shadow is at 0 feet, where is he sitting on the Ferris wheel? Well, one point would be way up here on top. So that would be one place he could be. So this would be a position of 0, or it could be at the very bottom of that. So for question 1, I want you to be thinking about, we're still rotating counterclockwise. But if we call the axle 0, he's at 0 or above or below the axle at 2 places. So one answer for question 1 would be at the top of the wheel, or at the bottom of the wheel. So those are the 2 places where his shadow would be called at a position called 0, at the top of the wheel or at the bottom of the wheel. In our previous work for question 2, we counted our time once Carlos passed that furthest right position, which would be position A on this Ferris wheel. And the question is asking you, if we count that as the time starting at A going counterclockwise, how long will it take Carlos to be at the position described in question 1? Well, at the top and at the bottom, the question is, how long will it take to get there? Remember, it's 20 seconds total. So at the top, if this is 20 seconds to go all the way around, it would be 10 seconds to get to position F. So this would be 5 seconds at the very top. And then this would be 15 seconds at the very bottom. So that's in 5-second increments. So at the top, it's going to take 5 seconds. And at the bottom, it's going to take 15 seconds. So just getting that in your head, that we are talking about going around on a Ferris wheel and rotating counterclockwise a full 20 seconds. So 5 seconds the highest point, 15 seconds the lowest point. Those are not lettered points. Okay. Also notice on this diagram you have A, B, C, D all the way through J. So if you were to count by 2s, this would be 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. So notice these are, in terms of seconds, different values, and we're just counting by 2s. So you could number all of these letters here by 2s. So those are 2-second increments, and that puts us all the way around. So the top and bottom are not, they're odd values, but we have those amounts that we can calculate. Alright, the next page talks about can we go through and fill out this table. So Carlos, or question 3, calculate the location of Carlos's shadow from center at the times given in the following table, where t represents a number of seconds since Carlos passed the position. Keep track of any patterns you notice, and as you calculate them, plot the location on the graph. So I want to go through and look at a couple of these with you, and then talk about the next page and get you prepped to finish this task, and also finish the Khan Academy work. So notice, if we look at the previous diagram, and these problems, hopefully I can show you both. Notice on this diagram, you certainly have some values that are similar. So it's going to have the same shadow distance at J and at B, so at 18 seconds and 2 seconds. So I'm going to mark on this chart that there is an 18 seconds, but there isn't a 2 seconds, so that's not the same. But I want to mark on this table which ones are going to have the same location, so we'll have the same value. If I look at letter C and letter I, that's at 4 seconds and 16 seconds. Those are the same. Letter D and letter H would have the same X coordinate. They're just above and below each other, so that's at 6 seconds and 14 seconds. E and G would have the same, so that's at 8 seconds and 12 seconds. So I'm going to write down for 8 seconds, this is really letter E on the diagram, and at 12 seconds this is letter G, and those are going to be the same. Okay, so I'm going to code those by putting a little 1 in a circle and a 1 in a circle. Those two go together. Also, are there other ones that are the same that we could mark on here? Well, notice B and E at 2 seconds and 8 seconds. B is to the right of the axle so far. E is the same distance but to the left. So if I knew what B was, I could put a negative sign in front of that and find what E was. So that's going to work out. So I can do the same for C and D. C and D are going to be opposite values, but they're both the same distance from 0. That's at 4 and 6 seconds. We also have 14 and 16 seconds, so that's H and I. Those are both 14, 16. So this is H and this is I. These are going to be the same, but one's going to be negative. So just trying to think about it. There are ways to fill out this table and try to be using some of that symmetry for this problem. So let's just look at one of those that isn't. Let's start with 1 second. So if I were to go through on this Ferris wheel and go 1 second, I would be right here. And if I make that diagram, I know the radius of my Ferris wheel is 25. I know that angle, that every second it was 18 degrees. So this is going to be 18 degrees. And I want to find this shadow distance right there. So the math I would do to find that value would be the cosine of 18 degrees equals the x value over the hypotenuse. And then if I calculate that, if I solve for x, I'm getting x equals 25 times the cosine of 18 degrees, and that'll give me a value. And if I know if I have that, I would also have one on the opposite side, which would be way over here at 9 seconds. It's not in our table, but those would be the same. So if I could figure one out, I could figure the other one out. If I did something similar, I could go up here. Between 2 and 4 seconds would be 3 seconds. I could draw that triangle. But notice for that triangle, we still have the same radius amount, 25. But this angle is 3 seconds later. So it's going to be 3 times 18, which is 54 degrees. And that's going to be at 3 seconds. So I have that value in my table. So it's going to be the cosine of 54 degrees, which is tripling because it's 3 seconds past that horizontal value. And it's going to be x over 25. So notice we get that same kind of pattern that shows up, that I get x equals 25 times the cosine of 54 degrees, and I get a value there. And if I wanted to go through and keep on doing that, notice all of these values right here in that table become more and more the same. So if I want to go to 8 seconds, my value of x, which is where I am from the shadow, is still going to be 25 times the cosine of, and I'm 8 seconds of rotation, so it's going to be whatever 8 times 18 was, because it's 18 degrees per second for 8 seconds. And I could do that for all of these values. So it's going to be the same radius times the cosine, and it's going to be the time times 18. Fairly similar we did with the sine value. And if I go to 18, which would be almost all the way around the circle, or 20, which would be a full circle, notice we'll get some answers that hopefully won't be surprising. So I'll write down one more of this. I'll calculate that. I'll show you in a minute. And then we'll come back and talk about the rest of this. So here are the values. Notice you have these x coordinates. Some are positive because you haven't rotated out of the first quadrant. This one is negative at 8 seconds because you're all the way over in the second quadrant. And notice the very last one at 20 seconds you were back at 25 because that's a full circle. The next page, 48, wants you to do two things. One is, can you write a general equation for finding this location? So I'm going to call my equation y equals, just for the vertical axis y, and it's certainly going to be you are 30 feet off the ground, but notice the 30 feet off the ground doesn't seem to matter because we're going sideways. So 30 is not necessary like it was for sine. All we're really doing is 25 times the cosine of 18 times the time. So be aware that although we had the 30 for the sine value, it doesn't make any sense to have that for this problem because we're not going higher and lower based on the axle. We're going sideways, and it doesn't matter how high up you were from the ground. Cosine, as a Ferris wheel problem, only deals with the left and the right motion, not the up and the down. They want us to go through and graph for question 4 this position. So at time 0, you are all the way furthest to the right, 25 feet. So at time 0, you're at 25. And then if you go through and start rotating, a full circle is 20 seconds. So 20 seconds later, you are back at 25 feet. So those are 2 points. You're halfway around the Ferris wheel at 10 seconds. So at 10 seconds, you are at negative 25. That's your x coordinate. So plot that point down here. And keep in mind on the other page I showed you on that picture, when are you at point 0 at 5 seconds and at 15 seconds? Plot those points. So at 5 seconds, you are at the axle location horizontally and at 15 points. And if you make a nice smooth curve, not a V-shaped thing, this is the graph of the cosine. So the cosine curves down, you're headed towards the axle, 0, then you go furthest left, you swing around, you're back at 0, and now you're back to the right at 25 feet. And if you did that one more time, you could go 20 more seconds. That puts you at 40 seconds. So you're going to be stopping here. At 30 seconds, you're the furthest to the left. And at 25 seconds, you're at 0. And at 35 seconds, you're at 0. And this is another graph of this cosine function, which does look an awful lot like the sine function. Keep in mind, sine and cosine are co-functions. Therefore, their graphs are very similar. So the rest of these questions, they want you to go through and sketch these graphs. So notice you do have a simpler version of this equation for number 2, or for number 6 rather. It's 2 times the cosine of x. So you still have a value here where it's giving you just x, not 18x. So at 18x up here, or 18t, it was 20 seconds to go all the way from one full rotation. So that means your period was 20 seconds equals the period. So that's how much you needed horizontally to draw that graph. Here it's just x. So if you're having just the cosine of x, x has to go 360 degrees because 1 times 360 equals 360 degrees. So it's going to take 360 is going to be your period for this graph. Because that's the horizontal amount needed to show one of those cosine graphs. 2 is your radius, so do your best on question 6. Careful on number 7, they give you a negative sign in front, so that's going to be an x-axis reflection that also has this plus 2, which means the graph is going to be shifted vertically up by 2. Question 8 and 9 ask you to go through and say, alright, what if we have these graphs? How could you take the most basic graph? So it might be helpful to grab Desmos and type in just y equals cosine of x and be in degree mode because we're going 360 as a full circle, and think about how would you take the parent graph and how would you manipulate this equation to make that picture. And the same thing for number 9. Grab Desmos, type in y equals cosine of x, and then ask yourself, how can you change either the coefficient in front of cosine, the coefficient in front of the x, maybe do plus or minus at the end of the function to make that graph. So mess around with Desmos, that's going to be helpful. Otherwise, we'll talk more about this at our next Google Hangout. And I don't know what you have planned for the rest of your day, but I'm going to eat a little more tortilla